Hey everyone, welcome to today's seminar. It's my pleasure to introduce Sophie from IRIF in Paris, France. So you're a postdoc there currently at the Malinka project, Mathematica Lingua Anche, I think. And without further ado, you're going to tell us about foundational aspects of size and dimension in higher categorical structures. Please take it away, Sophie.
Thanks.
Ton nom est français, Del Phalange, donc.
Sorry?
Ton nom est français.
Oui.
Donc c'est Del Phalange.
Des Phalange.
Del Phalange.
Yeah.
Okay.
Yeah, it's my pleasure to be here. Thanks so much to be there and before I talk about the proper talk, I'd like to say a few words on the Malinka project, of which I'm part, and for which I'm very grateful. First for the funding, of course, but also for the environment it provides, because so it's a very multidisciplinary project where we work with linguists, computer scientists, mathematicians. So Malinka stands for Mathematicae Lingua Franca. The guiding sentence that summarizes the objective is bridging the linguistic gap between the mathematician and the machine. Which is a very ambitious and compelling project, and that is mostly relative to the formalization of mathematics. So it's amazing to have these teams because linguistics, computer science, logic, and mathematics all developed separately as those last decades, and so it's very interesting to now work together in with the same objective, that is computer verification of mathematical proofs. And so so my personal hope is to contribute in this project by help bridging the gaps between mathematical practice and formalized mathematics at but maybe more specifically at the level of category theory and type theory. Of course, we want to use higher category theory. And so homotopy type theories. So I think there are many gaps to be filled, and so it's not only linguistics, some of them are also conceptual, and and I'll try to say more about those gaps today. And so, yeah, maybe the actual objective is to clarify the relationships between those things.
Sorry, this is very nice. One question by a philosopher seemed to say here that formalization of math belong to implementation with the machine. So we need to formalize to implement the machine. This is certainly clear, but this is a necessary condition for implementing. But this does not mean that it means that, no, this is the question. What do you think? That formalization is only useful for that, or there is also, so to say, a foundational use of formalization and the epistemic use of formalization. Formalization can help us to understand even without the machine, etc. So for you, formalization is simply something that has to do with the implementation of the machine, or is also part of the practice. What makes strange here is that there is no formalization on the side of mathematical practice.
Actually, it's great that you asked the question because yeah, I think this word can have different meanings, and I think that clarifying the meaning of formalization also is part of this clarification that is needed, and because yeah, I just wanted to talk about this right now, actually, because so there's a what does formalization means, and so here I'm mostly interested in the formalization of higher categorical structures, so higher category theory. And so, yeah, it goes, yeah, okay.
Sorry, if I have reconnection there, it's not possible to speak. There is someone connected by Zoom?
I'm not sure. I don't know.
But because
Yeah, I can see.
it can write down. It's because now they move the camera. Fantastic. So you can go.
Technology.
And yes, technology about.
It's digital.
It's you.
It's
You and the technology.
That's
Okay. So the heart of the matter to me lies in set theory because of the lack of common definition of a set, and so if one wants to formalize set theory, on the one hand we have type theory, that is like an abstraction of set theory, and the topos theory, also a formalization of set theory in a more mathematical sense. And so topos theory has an internal is equipped with internal logic that formalizes Boolean logic that is attached to set theory. And so in mathematics there is also formal category theory. So for those who were there on Wednesday, I talked about it a little. We have formal category theory, which is a sort of two-topos theory. One first question is what is the equivalent at the level of type theory? And so there is synthetic categorical frameworks that exist. And all of this is mostly related to homotopy type theory. So my objective is to understand the relationship between all of those things, and notably for higher levels of category theory and the formal equivalent and the relationships with homotopy type theory. So yes, maybe first of all, yeah. So there are several challenges in the formalization of higher category theory, and so I have identified three. So one of them is the question of coherence. So because in a higher dimensional framework, yeah, we want everything to act in a homotopy invariant way, isomorphism invariant, etc. And so there's a question of coherence that can be very difficult, and that is often the focus of higher category called formalization. And there's also a question of language and the question of size. Is it? Okay. And among all of those challenges, I think that language and size are some things that constitute the gaps between mathematical practice and formalized mathematics. Why? Well, first for the language. So yeah, well, at the level of the linguistic challenges, there's those different frameworks that are used on the one hand by mathematicians, on the other hand by more text theoretical communities, and that are not always gathered into something common. Yeah. And on the other hand, there is a question of the status of a mathematical statement. What does it mean? And so, notably, mathematicians do not use meta languages and talk in terms of definition and examples, while logicians talk in terms of yeah.
Yeah, I'm sorry, didn't want to interrupt, but why are you leaving coherence out of the concept of a gap between non-formal and formal mathematics? And in my experience doing some formalization, coherence is like one of the main issues I feel in translating non-formal proofs into formal proofs. Trying to get.
Oh, okay. I can include it. I wasn't aware that it was a gap. To me, it was a common problem that was addressed in something similar, but I am much more on the side of mathematics than formalized stuff. So it's just me ignoring the yeah. Okay. Happy to know more about that, by the way. So there is this question of language, yeah, and and status of a mathematical statement, and yeah, and what I like to focus on today is the question of size. Which will be the lens through which I like to compare frameworks. Yeah, and I guess why also do I think that the formalization of higher category theory is something useful for for mathematical practice, because it can also be taught. Why? Higher categorical structures. And notably, my focus would be on truncated structures, so n-category theory and truncated homotopy types. Why truncated? So a large amount of mathematics actually lies within a category. So can be sets, cosets, vector spaces, chain complexes, manifolds. So there's a lot of categories in which mathematicians work, and more actually a lot of mathematics happened within two categories. For instance, there are physicists that use these two categories of categories enriched over vector spaces. Yes. Okay. And a common feature of all of those categories and two categories is that all of those categories are not small in the sense that I will recall after. And more than that, if you look at the two categories of vector spaces and enriched categories, not only it's not small, but as a category of morphisms between two objects is not small either. So it's very big. Yeah, so those are very large structures. And so my objective here is to formalize the notion of a very large, very n times large n category, and show that truncated types in homotopy type theory are not formalized in a way that allow for the formalization of very large structures. Okay. Okay, so now I recall the definition of a category. So what we usually find is a category C consists of a collection of objects so we write. Okay, I could have used this one, but I like the type theoretic notations. Okay, for an object. Okay, and for each pair of objects, a set of morphisms from X to Y in C. Okay, and we also require identities. I will not focus on that. So identities, a composition, and additional data that ensures that all of this is associative, unital, etc. So there's a way to picture this, which is by drawing some points. And so here, X, Y, Z, A, objects C. And if I have an element of the set of morphisms, I can draw it as an arrow. Okay. G. And the composition so consists in providing something like that. So we require an equality here. And so the coherence here ensures that we do actually not need to draw the composites to obtain a significant notion of this writing, just F, G, and H, meaning that there is a unique composite that's from which we can go from X to A by using F, G, and H. So here, the associativity consists in. So if I take binary compositions, we can see here that there is two ways to go from X to A by using those composites. So the first one is by using this one and this one. Second one, that one. Okay. And so so it actually requires that this one and this one are equal. Okay. And so now we can already see why categories and spaces are strongly related. So okay, I choose the idea of higher categorical structures is that instead of having equalities here that establishes a composite, we take additional structure. So instead of having an equality here, we will just have a two morphism. Okay, but now I have two different ways to go from there to there. And hence we can also have a three-dimensional stuff like that ensures another coherence. And so there are a lot of different ways to encode this combinatorial data because there are more and more complicated coherence as the number of dimension raises. But in any case, we will always end up with a structure that is given by so a set in the more simple way of zero cells, which will be the objects, then a set of one cell, which will be the morphisms, etc. N cells, and it can go up to infinity. So here, in any cases, I will have and we'll be able to take some objects. And I'll also be able to form a subset or a subobject here. And the way those cells compose and arrange with them others is so often encoded by using presheaves or geometrical shapes that are, for instance, simplices. So you can use triangles. There are also blobs. So very combinatorial structures. And so here, won't interest in those way of composing stuff, and I will mostly be interested in what's a collection, and yeah, and what's a set.
But okay, so all these objects you want to see and to see infinity, all those are objects of set.
Yes, I will talk about generalization later when we can actually do that in a topos, or but for now, the most basic way to encode higher categories is yes, but it can be something else.
Just that you were using collection and set here, two different words, but you're using the same type.
So precisely to emphasize that there is a difference. Yes, exactly. Because so, okay, I forgot to give the most important example of the category of sets. Okay, so sets, so objects are sets. And for X and Y, there is a set of functions that compose and have an identity. So sets form a category. So yes, so now if we think about what is a collection, well, it can be a set because sets form a category, and there is no set of all sets. And set is not just a category, it is a category that is the most important to formalize the notion of a category because it appears in the definition here of a category. And so there is an intrinsic relationship between sets and categories that is definitely ignored. And that's why at first appeared the notion of universe.
You need the notion of set to define categories in this approach. So when Jean-Pierre Marquis come here, I tried to give an alternative definition of set using categories. And so don't you think that we can have a intuition of categories, a definition of categories that does not use the notion of set? So you think?
I think that we can define a more general structure than a category.
By the way, in the end, you take the liberty to speak of a collection of objects.
So this is
But why you don't speak of a collection of isomorphism?
No, because I will change the collection and propose another definition later. But this is just
Yes, but why you need that the isomorphism from a set?
the morphism. It's just a definition. I mean, just it's the way I see it is that sets form just the level that is just the level upper the one of truth values, and so at some point you will need something to compare your objects, and when you're within a set, you have an equality between objects, and so if you don't have that, you just go into infinity structures and in practice, the notion of a set actually is very I mean, it arises everywhere. Just
To clarify what is a set, we need a very strong actions.
Sorry?
To explain what is a set, we need an axiomatic definition that includes several axioms, including a action schema. So it's not an innocent notion of set. It's very, very sophisticated notion. So if I need to buy set in order to...
Just as the category is, yeah. Of course it is, yes. Yes. So. Okay, yeah, so. Okay, so the way this issue has been addressed at first was by introducing the universes, and so saying, okay, there is no set of sets, but there is a big set of small sets, and so we just end up with a hierarchy of universes, of sets. And so but we have some things that serve the container for sets. Okay, so what's a set? No? Well, if I have a so if x is a set, then it has elements. Which we can write as x is of type x. And a feature of sets is that we can compare the elements by using equality. And so for each pair of elements of x, we have a truth value that expresses the equality between the elements x and y of x. Okay. Okay, and so, for instance, what is the set of functions? So the elements so an element of the set of functions from x to y consists of mapping an element of the set x to an element of the set y. And in a way that respects the equality, so that if x is equal to y in x, then f of x is equal to f of y in y. Okay, so now to have an actual set of functions, we need to give what is the truth value that expresses the equality between two functions. And it is, so two functions are defined as equal if they are pointwise equal, and so that they have the same value and the elements sets. So okay, so actually
Product also runs on y.
sorry?
Product also runs over y of type x, right? Yes.
Oh, sorry. Oh, yes, sets.
Okay.
Yes. Okay, so there's okay, so this was the first representation of a category, but actually we can also give one that is more suited for the category of sets, for instance. So if I have a set X, which is an object so of the category of sets, then it has elements. And those elements can also be an element of X is the same as a function from the set with one element to X. After that, a function from X to Y will consist in associating an element of of y for x element of x. And so y. Okay, and now what's also can be defined as a set will have truth values. And so within there is false and true, the most basic case. And true is actually inhabited, whilst false is not. Okay. Okay, and now so set itself is an element of the yes.
Yeah, this is not necessarily the notion of set that I feel like first comes to mind to me. Like when I hear set, I usually go right to like ZF or something. So I was wondering, sorry, if are we thinking of these as like set as like the collection of discrete types, or is it like a Bishop style set theory?
Exactly. Yes. Yes, it's precisely a more maybe a little bit more formal version of a set that fits Bishop's one, and but it also provides the notion of a setoid.
Okay.
Yeah, and making the equality explicit actually allows for a lot of stuff. Very convenient to define quotients, for instance.
Okay. Thank you.
And yeah, the main interest, see that it generalizes at all levels to provide the notion of an n category, following this exact same scheme. Okay, because set itself is an object of Keck. And so now if I have a category, C, when is it small to me? Well, if there's a set such that the objects of C actually form a set. So and if in this like representation, we can see that when a category is small, you don't have the same level of internality that's possible, in the sense that C being small means that you actually take something from sex and put it outside of it, and so you lose a level of depth in the nested structure. So okay. Because an element is just something that is basically just one point, while an object of a category have actually more structure. So C small. And so now the idea is to formalize or generalize all this. And
It's a question. Can a set be a member or an element of another set?
Sorry?
Can a set be an element of another set?
No, really just a set. Can a set be an element of another set? No, or it loses its structure of set and it becomes just an element of a set. But unless you have something like a set of subsets, where here you can, okay, you have a set of subsets. This is possible because you have an equality. But having a set of sets is actually something very unnatural from the point of view of category theory. And
but one thing is to say that category theory need to admit or elements, set with super elements, and that I think that another thing is to say that category theory does not admit set that upset as elements. This is much more strong. This is much stronger as a sentence. So the fact that you need the set with your element in category, okay. The fact that you need sets in category theory, but you don't need a set of set. Yes, a set of set. I don't know, seem to me a little bit.
But that's Mackay's.
Sorry?
Mackay's set theory, does that teach you? Sets are only composed of order elements in Mackay's volts. There are no sets of
Mackay.
There are no sets of sets.
Any set is a set of elements. So you do not have a set of sets.
No, what you have is
The set does not form a set.
that's right.
But there you need that you have a set of morphism.
yeah, but so to actually
The set of a morphism, what is? It's not a pair of that.
Morphisms are now atomic objects.
Now is atomic object.
They are also order elements.
Okay.
In the Bishop style I'm more familiar with, you're allowed to have, I think, sets of sets as long as you have as long as it's like a bounded restriction, like there's a bigger set, like you were saying,
Yeah.
sets of subsets, as long as you have.
Right.
So be set living
It doesn't have a general union axiom. Because right, you just can't take a union of an arbitrary
Yeah.
collection of sets. It
But
has to already belong to a superset.
But now we come back exactly to the presentation of Jean-Pierre, that is Mackay theory of set. And so now, in order to have this conception of set, you need to define these with categories. So you don't need a set in the definition of categories. Or you need a set with your element, but then the construction of Mackay is based on the idea that using category theory, you can give a theory of set. No?
Mackay's definition of formalization of
dependent
categories
types. What he
uses
calls
sets of
sorts.
objects as well. But
And then he formalizes category theory in it, but he doesn't presume category theory. It's a first order. This is a first order language. Without no presumption of categories.
So the sets there are Mackay sets. That's what you want to say.
I think so. I
Okay.
think that's the way to think of it.
Okay.
Yeah.
And that the Mackay set can be defined without using categories.
Yes.
Okay. And then you can use them to define a category.
That was
That
kind
is
of
the idea.
that was more or less Mackay's project. was to say
Okay.
you
And
can do
this would be consistent with the fact that what she said is that you need to be set in order, if I understand well what she replied, in order to use the extensionality axiom, essentially.
Mhm.
And that Mackay set satisfied the extensionality axiom.
I don't know if I want to say that.
I think yes. No?
He has a very weak theory of identity, so I'm not sure.
You're not sure.
Maybe we should let her continue.
Okay. No, but
okay, so the idea now is to abstract the notion of a set, and so one way to do it is by using a topos, and in a topos we don't have a. We use a sub-object classifier as internal truth values object, and the objects of the topos are internally enriched in this, which means that actually we have So is S is the topos. So a topos usually is taken as a category plus a lot of steps, and including so the sub-object classifier, which serves to have an internal logic in the topos, and from which the objects are enriched. Okay. And so we can do all of set theory within a topos, and just tell you more general notion of a set. And here, yes, so it's a category. So the objects, the corresponding notion of elements will be given by. So if X is an object of the topos, what will be considered as an element of this object will be a morphism in S from the terminal object of S to X. And so we have all of the same notion. And we can also go higher in the generalization, in generalizing the notion of a category, just by okay. So here, okay. So if C is a category, it comes with a functor that gives the sets of morphisms in C from each pair of objects. And so actually, we can just forget about the category of sets and consider structures like that. And we can also forget about sets and take two categories that is itself equipped with other structures that make all this possible. Yeah. Okay. And this point of view is the one that fits the one of topos theory. Another way of formalizing that is so taking higher categories in a topos, like S being, for instance, spaces, or for instance, spaces. Or there is also the point of view of model category theory, model category, in which case we'll have, sorry, let's call it S as well, which is always equipped with an interval object that we will use to define the path from objects. And so any object of a model category, from any object of model category, we can define an object of path and a sub-object that will be that will give the equivalent of paths in the category. And something different from this perspective than this perspective is that here the objects are so C is an element of S. The path object is an element of S, and so the morphisms stay at the same level. And so this is the point of view that is formalized by homotopy theory, because models of homotopy theory are taken in this setting. Okay. So on the one hand, we have a formalization. The other hand, we have models. this word and this word are not the same. It's really a modern category. Okay, and in the same way, in homotopy type theory, for instance, we have universes that, in the most basic case, and without talking about subtleties, are displayed by a hierarchy. Okay, and one feature of this hierarchy is that so if I have a type that lies at level n, then the equality type so if X is in UN and X and Y are elements of type X, then the equality type of X and Y in X are in the same universe UN. Okay. So in particular, for the universe that at the level below, which is also to be seen as an element of this UN, we have an equality of types. And this one lies in the universe N. However, so we also have the equivalence type, which is a subtype of the function type. And because this map satisfies some properties, and because this is of type, okay, so this is a map, a function type in UN-1, so it's of type UN-1. And so actually, the equality type of types decreases a level and is in the universe UN-1. So because this is because it is equivalent because of univalence, of course.
So this is exactly just a callback to Steve Howley's talk not too long ago. This is exactly this perspective of local smallness via univalence that also came up in the discussion with him.
Oh, okay.
Just to remind people on that.
Okay, great.
What is the idea of equivalence you mentioned? You said equivalence X, Y?
Yeah.
Yeah. What is that symbol, and what is that you?
This is an equivalence type, so it's just so an element of this type is a type morphism from X to Y and a type morphism from Y X that's an inverse and another right in. So you ask for the definition of the equivalence type?
Yes.
Okay. So yeah, so we can just write it. I think there's
I don't need the formal definition if it is not necessary, just the idea.
Okay, so the idea is that a map F is an equivalence if there is a J a J and an isomorphism from G F to identity and a H together with an isomorphism from FH to the identity. So it's an injective definition.
Good.
Okay, so we have this asymmetry between terms and types, because on the one hand, the equality type remains at the same universe level, and on the other hand, it decreases the level because of univalence. And so now I'd like to talk about what does that imply at the level of truncated types. So truncated types are defined inductively, and so first a type is contractible or -2 truncated. It's just a point. I can give the formal definition, and then the type is n-truncated. If for all elements of this type, then the equality type of x and y is n-1 truncated. And so if we actually obtain, so we can let the type of R truncated types in UN as the elements of UN that are truncated. And sorry. Okay, so a type. So if X is in UR is n-truncated, to write that. So we obtain actually a double hierarchy. This is the dimension of size. And this is the homotopy dimension. That starts at -2 truncated. Okay, something that is R truncated will be R plus 1 truncated. So we have a sequence of inclusion like that. This, by definition, is the type of propositions in the zeros universe. This is the type of sets. It's an abstraction of sets, and it can be, of course, more complex than a set, but it's a hash set. Okay. This is one truncated types in the universe 0. Okay, and so we have all of that. And the question is to understand how all these relate with the others. And to what does it correspond at the level of the models and category theory? And one first remark that I'd like to talk about is that we usually actually take the convention of propositional resizing that requires all of the prop types to be the same, so that we can actually forget about this whole hierarchy of propositions at the level of -1 truncated tape, and only work with propositions in the first universe. This is the type of big sets in relations to what I said just before. So we arrive here to a type of n big sets. Sorry. Big propositions. Okay. And yes, they're actually just taken to be the same each time. And so we just did this one. Now, there's an important fact that is that the universe of n-truncated types is n+1 truncated. And so we obtain that the n-truncated types at level R are in Sn. And so I'm interested particularly in this type. Okay, so remember, this is the first level of sets, that small sets, and so this is small sets, and so now what we learn from this fact is that small sets just form a big category, and on this diagonal we actually have some stuffs that are in the dimension of okay. Okay, so from the point of view of category theory, all of what is below this diagonal is actually too big. It's like sets that contain small, all of the small sets are elements. So, and which can rather be seen as a category. Okay. And all of what is up the diagonal is actually small. Like, so if you take an truncated type here, by definition, it's the equality types of its elements will decrease a level. Okay, and this fits the model of n-category theory that is formalized by using a set of 0 cells, a set of 1 cells, a set of 2 cells, etc. Instead of decreasing the size of the objects as it appears on this diagonal. And okay, so now actually all of this this is we can form in most of the universes or most of the formalization of universes from a type in the universe 0, we can form a type in the universe 1, and etc. So actually we can just associate that. And okay, so in the same way, so the idea is really to focus on the elements of this diagonal, and so yeah, there is just a remark I wanted to say. Yeah, so the elements of a set just form a set, right? And so the objects of a category just don't need to form a set, but rather form a category in the exact same way than the elements of a set form a set. And so actually we can define
1 second. The elements of a set form a set because of extensionality, because we can say the two sets are the same if, but the objects of a category do not form a category in the same sense, because in order to know what is a category, we need to know also the morphisms and how the morphisms compose, and we need more information. So the objects of a category do not form a category.
If when the category is defined, they do.
They don't, because you could define different categories with the same collection of objects.
No, because I don't use the framework of collections.
It doesn't matter. What does it mean that what does it mean that the objects of a category form a collection?
To me, it means nothing.
Okay, so the objects of how do you define a category?
By the data of its objects and the spectral contours that gives.
Okay, so you have one portion of the data is the objects. So if you want to define to me a category, you have to give me this data.
Yeah.
Okay, now I can take this data and I can take the objects that you gave me as data, and I can define different morphisms and define a different category that is going to have the same objects because you gave it to me as a data. So the objects do not form a category.
What sense are they the same objects? They're in two different structures.
In the sense that you gave me the objects as part of the data. So if you gave me the objects, I have to be able to identify what objects they are. Because otherwise, how do you give me the objects?
They're in the category. Like, there's no inter-type identity. So
yeah, exactly.
Yeah.
If you think of a category of a set-based structure to which we have an equality between the objects, and what you say is probably true, and just but if you don't, the precise way in which you can compare the object is just given by the structure of the category, and so it is comprised in the definition of the category, and there is no other. And so if you form another structure, that means that you will provide another way to compare compare these objects, and it will be a complete different structure. Like you would have formed something else, and there is no. You cannot compare. Maybe you will be able to define a functor between those categories, and then you will be able to compare the objects. But
isn't there kind of danger of a circularity then? Like you already need the category to define it, right? So you can't just start with objects and then define a category, because without the category you don't even have, isn't that? I thought it sounded like a circularity to me.
No, it's just that you give a way to construct the objects, and then you give a way to compare the objects by using the level of sets that is below, and so it's and after that it forms a category, but you just construct the stuff first at the level of the objects and the morphisms, and
But you said you have a way of constructing the objects, and then you construct morphisms.
Mhm.
Okay, so you construct the objects,
Mhm.
and then you are going to construct morphisms.
Mhm.
Okay, I start in the same way as you. I construct the objects in the same way, and then I construct other morphisms.
Yeah.
Why can I do that?
for instance, if you but why could you not do that?
Yeah, and then because I have constructed my objects in the same way that you have constructed your objects, the objects are the same.
Oh.
You start with the object, so they are the same.
Let me give you an example.
Please.
Wasn't like when we tried to talk on structuralism, was it like your point, like the Klein 2 group is different than Zima 2 times Zima 2? Or like if you're under like a, I don't know what to say, sorry.
Okay. Then
So you can form like, and we can even actually stay at the level of sets. Like, so you form the set of natural numbers. Yes, so the objects.
how do I form this? How do I construct it?
So an object is like 0, 0, or say being just encode it. So you just give a way to construct a natural number.
Yes.
Okay, and then you have to give the equality between those. So you say that 0 equals 0, and zero is never equal to something plus 1. Okay, and the equality of m plus 1 and m plus 1 is just the equality of m and n. So you have set. And if you change the relation that is given by the equality, for instance, now I say, okay, so let's consider another set that has the same object. But let's say that, okay, if n and m are in n, then n of m and n are equal. Then my set is a set that has only one element and it does not have the same object. But the object that
But you cannot define that coherently, because then you will have that m plus 1 should be also equal to 0. So it should be false and true.
Yeah. 1 will be equal to 0 and I have a set.
No, but
sorry,
then
let me go like this. I form another set that has the same I just say that the equality relation is true everywhere, and I am perfectly allowed to do that. And then my set will have only one element, and
so you will have a 0 plus 1.
Yeah.
0 plus 1 will be equal to 0.
Mhm.
Yeah.
But at the same time, 0 plus 1 will be.
No,
No.
these are two different sets.
That's two different. Okay. The objects are, of course, the objects are not the same. here you constructed the object in this way, and there you constructed the object in
But because
way.
okay, and so now if we go at the level of categories, it's exactly the same. Like it's just that here I got this. If I change the relation on the relations and the objects, then I have no the relation and the object is that made the construction precise and that allows for a comparison between the objects and
okay, yeah, but here you have constructed the object, the natural numbers. Now we could keep going and construct morphisms between natural numbers. And we can do it in different ways. Okay, so the objects of these two different categories are the same because we have just constructed the mass of them. Small.
Because it would be a small category.
Okay, but
and so the objects will actually form a set.
Okay, still, it is true that even if it is only for small categories, the objects do not determine completely the category.
Yes, sorry, what do you mean exactly?
That the objects do not form the category. The objects are part of the data that you need to define a category, but the objects themselves do not determine the category because you could have different categories with the same objects but different morphisms.
Yes, this is exactly what this sentence.
But you said no before, sorry.
I said that the object not form a collection but a category, and just because we cannot distinguish, like the objects are not discernible as standalone entities, but only because of the relationships that they have the one with the others, and as just shown by this, there is a relationship. The object is more important than the way we construct the object themselves, because if we just crush everything down to one point, you can just say, okay, everything is an object of my set or category, but after that, if you say, oh, but they are all in a relations in one unique way, then we'll have an infinity number of objects, but in the end, you will just have a point.
Yeah, I think you both meant the same thing, but each time it was phrased in such a way that you could read them as negations of each other, but in fact, everything meant was the same.
Okay. Thank you.
Okay, and so yes, so maybe I can conclude. Okay, but I agree. I cannot say a category C consists of a category of objects, and no. It was not my point at all. It was just that in the end, once the morphisms will have been defined, the objects will form a category and nothing more than a category. But of course, I will not just yeah. Okay. Okay, and so in fact. Okay, and so the idea of the definitions that I propose is just to define an n category as the data of its objects, which are object constructors, and which I will not talk about how they are encoded now, but the objective is to just obtain internal truth values that just describe the process that is required to construct the objects. Okay, and which will be true each time. So the process that gives the object of X of C, and then n+1 functor that gives the n category of morphisms between each object, and that is the only way that we have to compare the objects apart from the symbol that is used to refer to it. And So and this thing has an inductive definition, which is just associating an n category of morphisms, and after that, the functorial part of this n+1 functor will give the composition, because okay. Oh, okay. Okay, and the naturality of this mapping will give the coherence.
Switch that off.
Okay.
It's disturbing.
And so the whole construction relies on the fact that we can prove that ket n-1 is an element of ket n, and which involves defining the n-1 functors and obtaining the structure inductively from the bottom. And so ket-1 corresponds to Boolean truth values, ket0 to posets, and then after you can just renormalize and take ket1 to be categories. But changing the -1 level and considering other truth values than true and false yields more general notion of sets, which are just enriched structures enriched over a truth value object. Topos. And this more or less corresponds to this hierarchy. Here it's n categories, but we can also do something more general depending on what is the -1 level that we choose at first, how we define it. Okay.
Thank you. Yes. You know.
So yeah, thanks for your talk. So I have a question about this picture, right? So this two-dimensional picture. So you know, you have this infinite sequence on the right and upwards as well. Where are they supposed to end? Is it just like a cannibal sequence, or could it be longer than that?
Sorry, what's the question?
Well, so if you go along size, for example, right? So
Like that?
yeah. So how many universes do you need? Just cannibally many, so indexed by natural numbers, or more than that?
I think the general case is indexed by natural numbers.
Okay.
I'm mostly interested in truncated type, so I'll need up to just for one n, but for each n. So
Right, because so one way to think about this universe is, right, if you come from more like the traditional set theory, is to think of them as like this thing called inaccessible cardinals, right?
Yeah.
But then in modern set theory, you have also large cardinal axioms that go way past inaccessible cardinals, right? So a worry that one could have is that, I mean, there's very interesting mathematics happening on the very far end, you know, of your diagram here on the bottom right, right? And yeah, I mean, I don't know if you have any thoughts about this, about like thinking about these higher axioms of infinity in the sort of generalized categorical context?
Yeah. I haven't thought a lot about it. I'm mostly interested in what could be like computer implemented, and so I don't know what's the status of those inaccessible structure with respect of implementation. But yeah, the question of whether one can reach infinity and how one is one to which I certainly do not have the answer for. Yeah.
Yeah, so kind of similar question, but in Coq, they like don't implement a natural number indexing. They only have like higher and lower and in between.
Mhm.
So the models always have to have like a dense hierarchy of universes. So do you have any sense of like what a model of something like that would look like here?
No, not really. Actually, there is I have no idea. I don't know. There's yeah there. What is true is that if you want to formalize the category of sets and that and then the two category of categories that contains the category of sets, you will need more universes than only three because of this structure that is intrinsic to the structure of even homotopy type theory, and because yeah, this is into this thing, and this is into the thing higher, and just because of the structure of truncation and universes. Yeah.
You are like, I mean, the last time I played with Coq is kind of way back, but can you actually quantify over this? Because if not, you can just observe what is used in the proof and then fix it leveling afterwards, and then you can get by with natural numbers again.
Yeah,
Because
you can
only
always encode. It's equiprovable to indexing by natural numbers, but they don't. So to do like a real good formal model, there are. They generally do. Yeah.
Questions?
What's the foundational aspect that you're most interested
What is the foundational aspect? Well,
in? That interests you most?
sorry?
That interests you most, it's most on your mind. There could be more than one foundational aspect, but here's the really one foundational aspect that to me is most important right now.
I think it's this thing. Like all truncated types are R+1 truncated, and also it is these decreases of degrees that is interesting to not even just what I'm doing myself, but just in homotopy type theory, when you have the equality types of even if not non-truncated, because of univalence, you have just for types in the level n, the equality type will be in level n-1. And because of the definition of truncated types, you have just for x at truncated level R, the equality type at level will lie at the level below, and this decrease of level in both of the directions is to me a fundamental aspect that is, even if left implicit, will just pop up because of univalence or anything, and so to me it's just yeah. And that also, yeah. And from which also we obtain the notion of a setoid just by as sets enriched over all the level below, when yeah. So this decrease in degree is to me the fundamental aspect.
So in the case of U00, right, that set, right? So there's an axiomatization of the category of sets. Do you also have an axiomatic characterization of U and N for every N?
Yeah. But it depends on what you call, but I'm using homotopy type theory universes to try to relate just what I'm doing with what is known and and how to think about it. How, but responsible. Yeah, it's just yeah, to me an element of in UNN. So it's by cat n, but which we can formalize as Tn. It's there's data of objects and an equality type, but directed at the level n-1 that satisfies additional, that is equipped with additional structures and renders this as auxiliary type n. And this structure is the one that is sketched here, and that is intended to provide the composition and the coherence by using functoriality and naturality in an inductively defined way, and which of course requires to define inductively everything, starting from the level of truth values and generating the level upper from that very first level of, so it's 3 minus 2. True. It would be like the internal truth value of T0, which would be topos, etc. And so the idea is to obtain a framework that relates topos theory and type theory.
Okay, yeah, I may have more questions about this, but thanks.
Okay.
Yeah, so.
Thank you very much for an interesting talk. I was wondering, does there currently exist a system in which this is implemented or can be implemented? Formal.
No, it's my project, actual project as a postdoc. I'm talking with some people who implement this on a computer. Yeah, it's ongoing.
You have a particular framework in mind of one of the existing systems?
I had the reason why I'm looking at that also is that I was wondering whether I could have something existent in homotopy type theory to derive my type from it. I'm not sure that it will be possible, but else starting from scratch also is an option.
Thanks.
Yeah.
Very challenging, yeah.
Okay, so if there are no more questions, thank you again.
We take the list.
Yes.
Yes. Yes. So.
Sorry.